Hello, thanks for being here. So yes, I hope to explain a bit about what HMSL is. So this is pretty much a history lesson in a way. This was a language that was from 1985 to 1990, so it's a look back at sort of what computer music was like in those days. So just to give an idea of a timeline for myself, in the late 70s, 80s, I was building analog synthesizers like this shoebox synth. Found it's a very cheap way to put things in a case. And then transitioned into sort of homebrew digital, like digital oscillators and so on. And then in the mid 80s into the 90s, was working on HMSL, which is the topic for today. And after that, left and worked on 3DO, building DSP-based, sort of modular software-based audio engines for a game console. Then in the late 90s, 2000s, I was working on JSyn, a Java synthesizer, Port Audio, which some of you may have used, a cross-platform audio library, a Web Drum, which was a multiplayer online system on the web from the late 90s. Then ended up working at Sony on PS3 audio, and then been working for over 10 or 12, almost 15 years now with the MIDI Association on the MIDI 2.0 standard, which is a new standard that's released, which I think will give us much higher resolution, more channels, more capabilities in MIDI. And then most recently been working on Android in the audio framework team. So I'm going to talk about sort of what is HMSL, go through some of the concepts and features, how it was recently revived by porting it to Juice, play some pieces, and then explain how you can try it out at home. So back in the 80s, sort of the context for this, doing live computer music in the 80s was pretty hard. There was no MIDI at one point. People were taking Casio keyboards and hacking the keyboard scanners in order to be able to control and generate notes from a computer. People were using single board computers. My first computer had 1 kilobyte of RAM. We had to solder our own MIDI interfaces. It sounded like I think we had to walk a mile in the snow or something. That's what it sounds like. People who want to write serial port drivers to do MIDI were writing assembly language, so it was harder than it should have been. And so the goal, we created HMSL and to try to address some of these needs. So HMSL is an experimental music language. It's ran on Mac and Amiga from about 1985 to the 90s. It was developed mostly at the Center for Contemporary Music, just across the bay at Mills College in Oakland. Myself, Larry Plansky, who's in the Hawaiian shirt. I'm in the white shirt. David Rosenboom, also, who's then went down to Cal Arts. So the goals was to simplify the control of sound, but without imposing any particular style. So we didn't want it to be like a jazz engine or a classical engine or a noise engine. It was just a toolbox that people could make wide varieties of music. And we wanted to explore different theories of abstract music, and we wanted to provide software tools so the musicians and composers could start making music without having to hack their own assembly language drivers. So the architecture of the system, the HMSL dialect, which is the language part of HMSL, is at the top. There was a thin host layer that allowed us to run on both Mac and Amiga. So we used a J4th on the Amiga and H4th on the Mac. So these were both written in an assembly language, 68,000 assembly language at the root. And then the output was on the Amiga. We had an Amiga local sound, 4-channel, 8-bit sound. We had a DSP-based system that could be added on, and then we had MIDI. And then same on Macintosh, we had MIDI, or the DigiDesign 56,000 for DSP. When we moved this onto Juice to revive it. HMSL was sort of in hibernation for quite a while, but I wanted to revive it because all this HMSL stuff was pre-web. And anything that's pre-web is kind of prehistoric in a way. And the history sort of goes back to the early 90s, and then it stops, you know. So unless something is sort of moved forward and put on the web, it kind of doesn't exist in a lot of ways. So we use Juice as a framework. The ME2000 synth was a ringtone engine that I wrote in the mid-2000s. P4th is a fourth compiler that I wrote in 1996. It's kind of a Frankenstein's monster of different software projects. The host layer is very recent, and then HMSL is pretty much unmodified. I really try to keep it exactly the way it was in 1985. So why did we use Forth? When I got my first Amiga computer, I was very excited, set it up, put my C compiler in on the floppy drives, 1 megabytes per floppy drive, compiled Hello World, and it took 2 minutes. And I just thought, this is not going to be fun. There's no fun in doing this. So I worked with Mike Haas and some other people on Forth, and the language predated us. But in Forth, you could write Hello World, and it would compile in milliseconds. You know, even a large music program could compile in a second. So there's a big difference between a 1 second turnaround and 2 minutes. And also Forth is live. You can just type into it, you can debug, you can do live coding. So for musicians, I think that interaction is very important. And it's also an extensible compiler, so we could take the base language and turn it into something else. So Forth was invented by Chuck Moore back in the 70s. It's reverse Polish, so it looks very, very different than most languages do today. It could either be interpreted or compiled. And basically the syntax is just words with spaces. So as the words execute, they operate on a stack. So if you type 17, you put 17 on the stack. You type dupe, it'll make a copy. 2 times will operate, you know, double the number on the stack and so on. So what some of the basic Forth looks like, and I'm showing you this because you can download HMSL and start experimenting with it. So I kind of want to give you a flavor of what the language looked like. So colon square is defining a new word that does dupe star semicolon. So that'll produce the square of a word. Then we have a do loop, which is kind of like a for loop. You can see the reverse Polish kind of coming in there with this conditional statement, and there's a program there to include code. So that is the foundation for the HMSL, and then we layered on top of it all these musical tools. So like shapes, collections, jobs, actions, players, and structures. So I'll go into what these different things mean. So the core data structure in HMSL is this abstract array of points. It's sort of like a vector in C++, and it's multidimensional. It's points in a multidimensional space. And we're using an object-oriented syntax here. It looks a little bit like Smalltalk. So you can do things to shapes. You can reverse chunks of it. You can scale the whole thing. You can scramble the elements. You can do transpose. So you can do things to shapes that are kind of composerly in a way. And then but the shape itself is just a dumb bag of points. It doesn't do anything. So we have a player which will play a shape in time, and it will interpret the contents of the shape and then play them. And then the instrument is what actually interprets the data. So one instrument might interpret the shape data as being durations, pitch, and velocity, and that'll be a melody, you know, a very traditional kind of melody. Another one might be interpreted as duration, harmonic complexity, and modulation depth. And it could be multiple dimensions, and it doesn't even have to have time. The time could be coming from somewhere else. So it could be very abstract. So one of the elements of shape that was, or of HMSL was a shape editor, and this is using a cross-platform graphical language that was part of HMSL. So you could run the same things on Amiga or on Mac. And I'm just going to really briefly show what that looks like. So when you fire up HMSL, you get this. That's the original look of it. You know, like I mentioned, you can type in commands, do your reverse Polish, and you can quickly just pull up shape editor here. So you can do things like you know, draw into it. We can select a region. We can reverse that region, lower it, raise it up. We can set a Y value and then invert it around that, or pick random points above or below that Y value, and so on. Or do you know, more complex kind of scaling operations. So that's the shape editor. So that's a part of HMSL that sometimes people might use that shape to be controlling other sort of algorithmic processes, and then they could be editing using this generic editor that's controlling these other processes. So collections were an important part of HMSL, and which is sort of where the hierarchical part came in. So HMSL had a hierarchy of composable objects. So the main objects were the sequential and parallel collections. So a sequential one, every time there are multiple children in the object, when each one would finish, it would play the next one. So it's very obvious. A parallel collection, when the last one finishes, then it will go on to the next thing. So you can have a sequential collection containing a parallel collection with a player and a job in it. When it finishes, it does player 2 and then player 3. So you can quickly create these collections, and then they can also be morphed and modified on the fly. So here's some sample HMSL code. And again, this is a programming language. So this is before MaxMSP, you know, before Ableton Live. It's if you wanted to use this, you had to write code. So people would often spend months or years sort of learning HMSL and learning, you know, how to program in this language. So this sets up a shape player. I won't go into the details, but sets up an instrument down here that every time it plays the shape, it reverses it and then plays it again, then reverses it and plays it again. So here's a piece that was written for Phil Corner, who was one of the Fluxus musicians in New York, and he was interested in HMSL. So in this piece, there's multiple tracks. One track, and it's an exploration of polyrhythm. So one track has one note per measure. The next track has 2 notes per measure. Another track has 3 notes per measure, and so on. And it's randomly selecting these measures. So one time it might play 3 against 7 against 9, and then it might play 2 against 5 against 6. And then another idea is that the measures that have the smallest subdivisions tend to be higher in pitch. So just want to play this. You may notice that there's sort of mirror symmetry, but you can also see in the visual. In this piece, there's several shapes. There's one shape that's holding the theme, and then another player that's taking the theme and then doing sort of random operations and sort of adjustments and modifications to that theme. And then there's a third player which is taking the modified version and then playing it sort of very slowly. So so I'm going to include hp:/xforms.fth. So it, oh, got to spell it right. Okay. So this is also using a pseudo-random generator, similar to what Bill was talking about. So I can pass in a seed and get the same thing again. Now, if I select the development theme, you can notice it tweaking and sort of modifying. Don't need this up here. Now it's gone back and recaptured the original theme. So I mean, these UIs look primitive, but it was, 1986, 1987. So it's another morph, as we call it, was our jobs, which will execute some arbitrary function. A lot of HMSL was writing little functions and then plugging them into these hierarchies as callback functions. So this would execute an arbitrary function on a period. And all this was cooperative multitasking. So the OS, the Amiga was multi-threaded, but the Mac Plus was just cooperative multitasking. Another morph is a structure, which used Markov chains to navigate through its child objects. Here's a piece called "Is It Borrowing or Stealing?" and this is by Phil Stone. And this was from a concert in '86, which was sort of the first concert of HMSL that, and we used with 3 Amigas, and we used a MIDI ring network, which Phil Stone was also in the hub, which they did a lot of things with MIDI networks. In this case, we'd be generating data, and then when we play something, we would also pass it on to the neighbor, and the neighbor could then borrow it or steal it, and then appropriate it in some way, modify it, and then what they did was passed on, and then we could steal. So we're all sort of borrowing and stealing from each other. So this is what sounds. So the sound that you're hearing is Amiga local sound. Since we were using fairly slow computers in those days, these are basically 8 megahertz, 68,000s, and doing it, almost any instruction would take 4 of those cycles. So they were pretty slow compared to the systems today. Couldn't do real-time audio, and sometimes just doing basic operations could result in sort of jittery scheduling. So the MIDI output was put into a timestamp buffer just slightly ahead of time, and then it was pulled out of the buffer, with sort of assembly language, low-level code that would pull it out of the buffer and then send it out the serial port. So we could get very, accurate timing output for MIDI using these timestamps. So there are a number of, wide variety of pieces that people did using HMSL. I just want to make sure I keep track of time here. Nick Didkovsky did a piece where instead of generating music, he was sequencing different fans that were blowing air and blowing these paper sculptures around. David Dunn was doing pieces in the field where he was recording, altering, and then playing back bird songs to try to engage in a dialogue with different species. David Rosenboom was doing work where people would play music into HMSL. He would parse that, transform the material live during performance. I had a piece called Swirl, which would create a melody which can be thought of as a shape and a pitch time space, and then it would apply just a 2D rotation on that melody. So a note that was at the beginning would end up sort of at the top in the middle, at a high pitch in the middle, then it would end up sort of at the end of the piece, then it would come back sort of at the low pitch in the middle, and then back to the beginning. So the melody is sort of rotating in space, then being played on Amiga Local Sound. Another one we did in another MIDI ring network, where each note was modeling a neutron, which could trigger a fission reaction in the other person's computer, and we would play the piece by raising and lowering control rods on the screen. And the thing kept blowing up all the time. I could not get this thing to stabilize. It was, I'd sort of inch the control rods up and it started to go, boom. And I thought, okay, most reactors don't immediately blow up all the time. And my Koss, who had wrote JForth with me, had been a nuclear reactor operator in the Navy. So I called him and said, why doesn't your reactor blow up? And he said, well, as you raise the control rods, the reactor expands, and then you're less likely to get a collision. And so I fed that back into the musical algorithm for the process, and suddenly, I could play it. And it was this nice, stable thing that I could perform with. So, so it was kind of physical modeling, but it was physical modeling of a nuclear reactor. The hub, which is, if you don't know the hub, please check them out. Amazing, pioneering network band, and they've been performing for a long time and do amazing stuff. And they did a number of HMSL pieces. So it wasn't a huge number of people using HMSL, but there are people who are generally doing. They would spend a long time, and they would do some pretty amazing stuff. Another feature in HMSL was the score entry system, and this allowed you to sort of create, score material, notes, for lack of a better word, but it was within a programming context, so you could, set up accelerandos, or you could incorporate random note generation in do loops, and you could also, play things in parallel and so on. We also had a just intonation system. A lot of people doing HMSL were into just intonation, and we could use channel rotation, MIDI channel rotation and pitch bend, just like is used in the new MPE standard, and we could do dynamic intonation, which is where there's no fundamental. So this note may be a 5-4 ratio, but it's not 5-4 to a fundamental, it's just 5-4 to the previous note. So the PR would play a ratio to the fundamental. This next one would play relative to the previous note, and then this other one would update the fundamental. So I'll show you what that sounds like. We'll go into the score system. Put a warning here that use words like C3, which if you're entering hex numbers, there'd be some conflict there. So I can just, I'm going to just refresh. I've left it in a different instruments from the previous piece. Predictable. So here. Okay. So, you can do these in a loop. Or you could just randomly choose a note. Something like that. So in this case, it was doing the channel rotation and then doing a dynamic intonation to play piano notes where there is no fundamental and the pitches are very fluid. So just sort of stretching the pitch space. Let's see. The control grids were used to create hyperinstruments, a very primitive version of what Bill was doing with Lemur. So you could set up grids and sliders and things that would work on both Mac and Amiga and then plug functions into those. So you could make things like little button grids like that thing up on the top. So a little bit of fourth code there on the screen. So this was a performance with a projection in the back. This was probably 1990, maybe, using the Amiga connected to a DSP system. And then I'll do a quick demo of something that uses control grids. This is Splorp. So, sorry, these things look a little small. The resolution on the older computers were a lot smaller, and I haven't scaled them up to fit on to take advantage of the much higher resolution. So, these are jobs that can be turned on and off. So we can control sort of overall sort of a target pitch. And then we can also control things like the harmonic complexity. So either it'll move in fifths, or then we can add major thirds, and then we can add in, maybe a fourth, or it can, move in increasingly complex, and then we can really get sort of a chromatic motion if we crank this up. We can also record these gestures into a shape. So these fader movements are being recorded into a shape. So we can speed it up, slow it down. Then play those back. And so on. So in order to, we wanted to restore HMSL. It was ported to a Windows system back in the 90s. which was lucky because it means that we got things off these old floppy disks, which have now gotten very moldy, and I can't read any of the old floppy disks, but we luckily had a current version of HMSL that had been ported onto regular hard drives. So we were able to rescue it, and I wanted people to be able to sort of experience what it was like. Also, there's some interesting ideas in there, and I think people, could have fun doing it. So that's why we recreated it. So P4th, the earlier fourths were all 68,000 assembly language, and 68,000 is not a popular processor. P4th was written in the 90s, and it was sort of the last fourth compiler that I wrote because it was written in C, and so I never had to write an assembly language again after that much. So, and P4th was sort of derived from the HMSL fourths, so it was easy to get HMSL to run on it. And then for the host dependencies, we had code that was, written in C for both Mac, or not in C, because it would be sort of fourth calls into libraries, but in order to run on the current systems, I wanted to use cross-platform code, so I'm using Juice to access the audio and the MIDI and the graphics. So Juice is a very nice cross-platform toolkit that a lot of people use for doing plugins. And basically, we just had I only had to implement these host primitives, open a window, draw lines, read and write MIDI, some clock functions, get the mouse position and get event. And then once these were written, HMSL just built and ran on top of Juice. For sound generation, MIDI was obviously an important tool. On a 8 megahertz 68,000 with no floating point, we could not do real-time synthesis. So the Amiga local sound was very useful. We could do 4 channels of 8-bit DMA. Could loop them and change pitch. Nick Dukowski did a piece with this where they used game theory where you bid on control of the spectrum, and if you want to win, you could bid more tokens, but the more tokens that were bid, you would have less control because the whole system would be divided by the total number of tokens, total number of votes cast. So it was this, weird sort of cooperative, competitive game in order to controlling the spectrum of the sound. That's Nick in the foreground there. So what people did was take advantage of the Motorola DSP 56000, which was a very important chip for a lot of computer music folks in this time. So instead of having an 8 megahertz 68,000, we had a 27 megahertz DSP, and with the fractional fixed point, it wasn't float, but you could use it, you could do things like you could with float, and it had saturation arithmetic, so you could really do a lot of real-time audio with these devices. So on the Mac, we used the DigiDesign boards, which were used for doing 16-bit record and playback and processing. And then on the Amiga, Steve Curtin designed this GMP board. And if we were talking to musicians, it was the General Music Processor was what it stood for. If we were talking to chip manufacturers and trying to scan parts, then it was the Guided Missile Project. So the meaning would change depending on the situation. So there's a paper for the 91 ICMC on that. What that did was really allow us to open up the sound possibilities and really have micro control of sound. But like from the Amiga, for example, anyone who wanted to do it had to wire wrap a connector between the parallel port and this GMP board and then solder the GMP board. So it still wasn't just plug and play, but it was worth it. So then to write a piece, you could use this 56,000 macro language, which is kind of a pseudo assembly language where you could define control rate code for LFOs and envelopes, and then audio rate code for the actual audio data path. And you had unit generators of filters and oscillators and things that you could call as macros from this language. So this, the one piece that we did in, this was a bit later in '93, used again a MIDI ring network. Jeannie Parson worked with Jeannie on this. And what would happen is we would play a note, and then that frequency would go out to the other player, and then the other player would choose their note frequency as a ratio of the incoming frequency. So it was again this sort of relative dynamic just intonation. You could also pick different carrier modulator ratios, and it would sequence through these different CM ratios in order to get different sounds. So that's what this sounded like. It's shrunk. I cannot see it. Yeah, this one. Good old FM sounds there. Kind of quintessential beeps and bloops. Another piece was Squiggle, which you could draw a 2D gesture with the mouse, and that would map to 2 synthesis parameters, and then that shape would then appear on a grid, control grid to the right, and then you could pick and play back these pre-recorded gestures in sort of a duet, and then control the DSP. So that's what this sounded like. There are a lot of comb filters in there. So that's a little quick tour of HMSL. It's on GitHub. If you go on GitHub and look for HMSL, you can download one for Mac. It was written in Juice, so I probably will appear on Linux and Windows versions pretty soon. It's precompiled. There are some guided tours, which I'm adding to, and please file bugs or join the discussions there. And anyway, I hope you enjoy it. Any questions?
Any questions in the audience? Maybe not.
Okay.
Yeah, thanks so much. That's incredible. Really love it. Like, it's so nice, like, seeing the history of computer music, and so much of it these days. You know, it seems like it's a very modern thing, but sort of having you and John here as well is like wonderful. Just having that sort of history of. I love the fact that so much from the Bay Area there was such a explosion of computer music around that time. So really, really nice to hear that. Thanks so much, Phil.
Oh, thank you. Yeah, thank you.